This is Bob McFettridge with Beckwith Electric. Welcome you back to our final part of session number 6 of our IVVC presentation. And this is the session where we are talking about how to coordinate regulator and capacitor controls in order to fully implement an IVVC system without the need of communications. And I'd like to point out that no animals were harmed in the creating of this presentation. So in review, we had looked at a utility in part 2 who was implementing a system, and in doing so they discovered 3 different problems that had to be solved. And this final session, this final part of the session, we'll discuss how the solutions were, how the problems were resolved. So to recap, the 3 problems were that they were using negative reactance in the line drop settings for the regulator and LTC controls to coordinate with the capacitor banks. So the theory was that both the voltage regulators and LTCs and voltage control capacitor banks would all be looking at the same voltages, would all have the same rails or bands, so to speak, and would have different time delays and to keep the coordination. And the time delays were set to meet two requirements. Requirement number 1 is that they wanted the capacitor banks to operate and take the majority of operations, and that they wanted the capacitor bank furthest from the source to be the first to close and the last to open. So in order to coordinate, they would use a negative X on the reg control, which would basically say that if the regulator or LTC saw the power factor get too far leading, which was an indication of too many capacitor banks on, it would induce the regulator or LTC to raise the voltage, which would in turn then turn 1 or 2 of the capacitor banks off. That worked well until they got to circuits that either did not have enough capacitors or had capacitor banks out of service due to damage typically from lightning storms. In that scenario, they would get low voltages because with a lagging power factor, the negative X would actually induce the regulator or LTC to want to lower the voltage to try to turn a capacitor bank on. But if there's no additional capacitors to turn on, you experience low voltage. The second problem was that in trying to coordinate the time delays on the different capacitor banks, they would have difficulty with controls either having the wrong settings initially, or more likely after they were installed somebody would go back and change them, typically as they were changing out a failed control. And then we would have miscoordination, which could cause hunting between capacitor controls. The final problem that occurred was due to sectionalizing. They were doing a lot of auto reconfiguration of circuits, and when you do that, capacitor banks that were on one circuit are now placed on a different circuit and therefore have to coordinate with a different number of capacitors and regulators, and that would also throw off the coordination. So with that in mind, we're going to look at the problem, and that is that we want to keep the power factor between 0.98 lead and lag, and we want the regulator or LTC to only correct for voltage if the power factor gets out of that area. So what was happening is if they had a voltage that would be mainly reactive, a load that would be mainly resistive, then you could have the case where you'd have too many capacitor banks closed and you can go too far leading. So to resolve that, the negative X would see that and raise the voltage to induce some of those capacitor banks to go off. But in lagging power factors, that would induce the LTC to lower the voltage to turn capacitor banks on, and if there were no cap banks to turn on, then you would end up with a low voltage. Looking at the possible solutions, the first solution would be to have the negative X only be applied in the negative direction. So only apply the negative X for a leading power factor and have it to where it would have no effect on the lagging power factor. That way we could still use the negative X in the leading direction to raise the voltage to induce a capacitor bank to go off. But if we had a lagging power factor, it would not impact the band and therefore would not drive the voltage down during lagging power factors with no capacitor banks available. The problem with this solution is that we are now treating negative X differently for the use of coordinating capacitor banks versus its normal operation for line drop compensation. And therefore, if a customer wanted to use it for line drop, they would want it applied in both directions. So that option was not selected. The second option was to cap the negative reactance. One of the problems with R and X is there is no cap. The voltage setting you put in it for X, for instance, if you put in a negative 10, it will apply 10 volts of compensation at full load. So if all the load current was reactive, it would actually increase the band center by 10 volts. Therefore, as the load goes higher, the amount of compensation continues to go higher. And in the case of the negative X, as you go further lagging, you bring the voltage down even further. So if we could cap that compensation, then we could limit the amount of effect it would have. Now the reason we need to go with a higher value of maybe -6 or -10 is because we need that slope in order to bias it. But we don't need the full voltage. So we want the slope of a -10, but we may only want to cap it for a 2 volt compensation in either direction. So as an example, if we put in a -6 with a cap of 2, then that would guarantee that the band center would never be biased by more than 2 volts in either direction. Once we got up to the cap, there would be no more bias applied. Leading power factor, then we are going to raise our upper band by 1 volt. We are not affecting the lower band at all. So in this case, with a band center of 122 and a bandwidth of 2, our normal band would be between 121 and 123. And if we exceed the VAR setting, in the example 900, then we will, in a leading mode, we will raise the upper band by 1 volt. What that will do is that'll make the voltage go higher before the LTC attempts to do a lower. So what we're basically doing is we're saying on a leading power factor, we want a capacitor bank to open as opposed to the LTC lowering the voltage. So if we have a high voltage with a leading power factor, the preference is to have a capacitor bank open to bring the voltage back down. So by raising just the upper band by 1 volt, we can then allow the voltage, if it's in this area, to still remain in band, but it would be out of band for the capacitor bank, and it would allow the cap bank to time to an open before the LTC took the operation. So we're saving both the operation on the LTC and we're getting our power factor back closer to unity. Likewise, if we go lagging, then we're actually going to lower the lower band by 1 volt. So in a lagging power factor, we want capacitor banks to come on, so we want the voltage to be raised by the capacitor bank closing as opposed to taking a tap. So if we lower our band by 1 volt and the voltage is somewhere in this area here, where we would have been timing to a lower, we no longer are. The capacitor bank will be timing to a close, and again, this will give the capacitor bank additional time to close. And if we are in band, then we have no effect on the band center or the bands at all. So if we look at it, with VAR bias, after a maximum time setting, if we have not come back in, then we will remove the bias. So in other words, if we were leading and we raised our upper band to allow a cap bank time to open, after a finite amount of time, if the bank did not open, thus having us see less leading VARs, the control will remove the bias, it'll be out of band, it'll take the tap, but then it'll generate an alarm to SCADA indicating that it attempted to bias due to the VAR flow and did not see the VAR flow change, therefore an indication that we either don't have enough capacitance on the circuit or one or more of our existing capacitor banks is out of service, both of which is valuable information. And then, if that's the case, the bias will not be applied again until the VAR level returns back to within normal ranges. Then the next time it exceeds, the bias will be attempted again. So, with the negative capped compensation, we are shifting the entire band. So the band center and both the upper and the lower band shift. They shift in a linear approach. So as the VARs are changing, the compensation is changing, and therefore the upper and the lower bands are changing. The problem with it is it does not have a maximum time, and it does not generate alarms to SCADA. So if we are biasing the band center in a direction to encourage a capacitor bank to close, and there are no more capacitor banks to close, we're going to be biasing the voltage lower, and that bias will remain in effect, and we may experience some low voltage. But by capping it, we can at least control what the lowest voltage would be. With VAR bias, we're moving one band to slow down the timing on the LTC or the regulator so that it remains in band while the capacitor bank is out of band. But we are doing this in a step manner. So it's you go from having no bias to full bias, not linear like the negative capped compensation is. But we do have the advantage that we can have a maximum time, and if we do not see the VAR's flow change in the way we anticipated, we can then remove the bias, act accordingly by taking a tap, and then alarming SCADA to the fact that the capacitor banks did not react in the manner we were anticipating. And this graph kind of shows you both. So here's our VAR bias, and you can see that the VAR bias is a step change. We go from applying no bias to applying full bias, where with the capped compensation you can see it is a linear approach. But notice that with the VAR bias, we are only biasing one edge, and the band center remains the band center continuously. And one edge will remain solid, and only the one edge will be biased. So for lagging, we will bias the lower, and for leading, we will bias the upper. But again, with the capped, notice that the band center is varying with the VAR flow. So in summary, with VAR bias, only one edge is being biased, where in the capped compensation, the entire band is being biased. Well, applying VAR bias or capped compensation worked fine until the customer went into voltage reduction, and then a new problem occurred. So either of those methods fixed the problem of having low voltage due to a lack of VARs and a lagging power factor. But in correcting that, a new problem was introduced, and that is that in voltage reduction, the customer wants the capacitor banks to be closed so that the voltage downstream is higher than the voltage at the source, therefore allowing a flat profile and allowing the source voltage to be lowered much more than it could be without the capacitor banks. But in this mode, we will have a leading power factor. And as we saw before with the capped compensation and VAR bias, a leading power factor induces the regulator or LTC to raise the voltage, which is counteractive to what we want by issuing a voltage reduction command. So, the possible solutions for that. If we're using capped compensation, we can flip the sign and be negative compensation while in normal mode, but go to positive compensation while in voltage reduction mode. That way, leading VARs will not allow the regulator LTC to raise the voltage, but will actually induce them to further lower the voltage if we have leading VARs, which is a good thing. if we're using VAR bias, what we can do is simply just disable the biasing of the edges while we are in reduction. So this next slide shows you that if we switch from negative to positive, now you can see in positive, leading VARs actually induce the LTC or regulator control to lower the voltage. So you can see here in VAR bias mode, we were inducing a raise, but in actuality for leading VARs, and that's what you would want if you're not in reduction mode. But when you're in reduction mode, you actually want to encourage a lower when you have leading VARs. The only way to have leading VARs is if the downstream voltage is higher than the regulator voltage. And if that's the case, that means the regulator voltage can drive lower and not have to worry about the downline voltage getting too low. So in this case, now the leading VARs will actually shift the bands down, and the upper or lagging VARs will actually shift it up. So this is beneficial in the case where you may have capacitor banks, but they may be offline or out of service. In that case, if you were doing a straight percentage voltage reduction like is typically done, and you were counting on the capacitor banks to support that voltage, and they were not online, then you could run into low voltage complaints when you went into reduction. But by using the positive reactance, if we have a lagging power factor because those capacitor banks are not coming on, then it will not allow the voltage to be reduced by as much, and therefore we will not have the low voltage complaints. So when we do have the capacitor banks online and they are closed and we see the leading power factor, we know we can actually drop the voltage a little bit lower. But when the capacitor banks are not online and we have a lagging power factor, we know that we cannot drop the voltage as low. So we're dynamically going to look at the amount of reduction we can do by the VAR flow. Now, after implementing this, the next two slides are going to show you the before and afters. So this particular case was on a feeder with single phase regulators, and this was pre, so using the VAR bias without disabling, or using the capped compensation without flipping the sign. And you can see that the target was a 3.5% reduction. When it was initially issued, the regulator tapped it down and reduced it by 2.5%, but because of the bias, we have the leading capacitor banks closing, driving it leading. That actually encouraged the voltage to be raised instead of lowered, and we got a net 1.5% reduction, not what we wanted. But after flipping the sign, we can see that when we issued a 3.5, we started at about the same level, but notice instead of losing, we actually gain more, because now as we go leading, we're actually encouraging it to lower the voltage more, and so we've picked this amount up. So halfway about is where you would have been if you weren't doing anything with the X. But with negative X, you can see you actually lose reduction, and with positive X, we actually gain reduction. This is the same slide, only in this case it was for an LTC, but we can see similar results. That net, in this case, we actually even got more reduction. In this case, because it was an LTC, they were only requesting 2.5%, and you can see that we actually got 3% because the leading power factor on the bus indicated that the circuits could handle the additional lower voltage. So that solved the first problem. The second problem the customer was having is in coordinating all the time delays. For the system to work correctly, the right capacitor banks have to operate in the right sequence. And that was being accomplished via time delay settings. And if the time delay settings were altered or set incorrectly, then you could have cap banks operating out of sequence, and that could cause hunting. In order to solve this problem, it was determined that the only thing the capacitor bank really knows about its sequence in the circuit is the effect it has on the circuit. So again, the sequence in the circuit is important because we want the furthest from the source to be the first to close and the last to open. Likewise, the one closest to the source would be the first to open and last to close. Therefore, each cap bank needs to know where it is in the sequence to know when to open and when to close. And it was determined that by looking at the delta voltage, which is the effect that a capacitor bank has on the secondary voltage when it operates, that would tell us its place in the circuit. Because if all cap banks are the same size, then they would all have the same effect on the circuit unless they were located in different places. Because the two impacts on the delta voltage are the size of the cap bank and the distance from the source. The larger the cap bank, the bigger the delta voltage. The further from the source, the bigger the delta voltage. So if I have all my cap banks the same size, the cap bank with the largest delta voltage would be the one furthest from the source by definition, and the one with the smallest delta voltage would be the one closest. So if we could use that information to help set our time delays to keep the coordination. But we need to make sure that we normalize all the sizes, because a 600 kVAR bank with 2 volt delta voltage and a 1200 with 1 bank would be the same distance from the source. So I can't look at just the delta voltage. I have to have the delta voltage normalized off the size of the cap banks. So we would have to pick one size, which would be the largest size cap bank on our system, and then nominalize the delta voltages of all the smaller banks. So in this case, we would double the size of the delta voltage on a 600 kVAR bank to make it equivalent to a delta voltage on a 1200 kVAR cap bank. With that in mind, and we've got it normalized, we can now do calculations. So if we had every control start with the same base time delay, let's just say 600 seconds, then we could divide that time delay, base time delay, by the delta voltage for the close time. And if we did that, that would ensure the bigger the delta voltage, the shorter the close time delay, and therefore the delta voltage, the capacitor with the biggest delta voltage would have the shortest time delay. Likewise, if we multiply a base time delay by the delta voltage, then the open time delay would calculate to be the shortest for the one with the smallest delta voltage, which again is what we want. So here's an example, and in this example, let's say we have two 600 kVAR cap banks. One of them has a delta voltage of 1 volt, the other 2 volts. If we look at the calculation, the 1 volt, the close time delay would be 600. 600 divided by 1. The open would be 600 divided by 1. Therefore, it's going to have the 600 for both time delays. Bank 2, the close time delay is going to be 600 divided by 2, which is 300. So its time delay is half, and therefore it'll time out to a close before cap bank 1, which is what we want. Its open time delay being multiplied, therefore the bigger delta voltage is going to have the longer time delay. It's now twice as long. So if we do this kind of philosophy by having the delta voltage be part of the calculation on time delays, we can keep the sequencing, and we can start with a base time delay, and then each control, without needing a time delay setting, can automatically calculate its own time delay off of its delta voltage. We can also use the same time delay calculation to help us with our voltage rails, our min and max rails. Obviously, if we have every cap bank set to open at 126 volts, we don't want them to all have the same time delay, or we may get multiple banks operating at the same time. So not only do we have to have different time delays for our open and close, but we really want to have different time delays for our min and max rails, and we can use the same principle for both. Now, we do have to make sure that there's at least 0.2 of a volt difference between the delta voltages on each bank to guarantee that there's enough time delay between any two banks. Because if we have two banks with the same delta voltage, they will have the same time delay, and we can get back into cases of hunting again. The other thing we have to keep in mind is we must have the delta voltage calculated correctly. If we have a bogus delta voltage for whatever reason, that will cause our time delay for that control to get out of sequence with the other time delays. Finally, our third problem was sectionalizing. And we'll review what we mentioned in part 2, and that is a typical feeder where these two capacitor banks are coordinated with this regulator, and this capacitor bank is coordinated with this regulator. So our time delays are set accordingly. But now if we normalize these at 600, but these were 1200, then we would be fine coordinating with our delta voltages in this direction. But then when we closed in, a delta voltage on a 1200 may be the same delta voltage as this bank, even though it's much closer. So we would have to nominalize these to that 1200. So it's very important that when we use this auto-adaptive algorithm and we're going to nominalize, that we pick the largest capacitor switch bank on the entire system and use that as the normalized value in all controls, so that we can reconfigure on any circuit and know that we maintain our coordination. So we definitely have to make sure that we do our normalizing. So in summary, the three main problems we had were solved by, first of all, placing new algorithms in the LTC and regulator controls via VAR bias and capped compensation, so that we could limit the effect of the compensation when we have the lagging power factor, so that we don't have low voltage conditions. We then had to address the coordination issues, and that was done in the capacitor controls by having the delta voltages become part of the calculations. And by doing so, we also solved the third problem, which was maintaining coordination of the system even when we were sectionalizing and tying circuits together and functionally moving capacitors from one circuit to another. This system has now been installed for several years, but most recently these new changes have only been done in the last couple months. But this utility has over 2,500 LTC and regulator controls and over 1,500 capacitor controls to date running this system, anticipating going upwards of 8,000 capacitor controls. Their overall goal was to be able to dynamically reduce load by as much as 400 megawatts, and currently they're already over halfway there, and they don't even have a quarter of their system automated with this new technology. So I hope this is enlightening. You know, a lot of people hear smart grid and they think that you can't be smart without communicating, and this is a good example of how you can achieve all the same benefits as a centralized approach without the need for communications. So we thank you for allowing us to present this material to you. If you find it valuable, please let us know. If you have any questions, you can submit them via the web portal, and we will have somebody contact you with answers. Or if you would like for us to come out on site and do a customized presentation, we'd be more than willing. Just call your regional sales manager and we'll make that happen. At Beckwith Electric, we really appreciate your time and value you as a customer. Thank you and have a blessed day.